Okay guys, we're ready to start the next chapter, which is a study in electric fields. In this chapter, we're going to be moving beyond single point charges, and we're going to be looking at creating electric fields for a collection of charged particles. Okay? So, let's start doing things. Now, when we start thinking about collections of charged particles, we want to concentrate on what are considered to be important charge distributions, because they're charge distributions that we create quite often and that we run into. Okay, of course the point charge is important, but we've already done that. We're going to talk about a dipole, which is an object which has negative charge on one end, positive charge on the other. We're going to talk about an infinite line of charge. Wires, if you're up close to them, can be thought of as an infinite line of charge. We're going to talk about planes of charge. Plates in a parallel plate capacitor can be modeled as infinite planes of charge. And then we're going to talk about fields of charge. Okay? So, point charge, line of charge, plane of charge, sphere of charge. Now, recapping, in last semester we know that the electric field caused by a single point charge uses the following equation. The electric field is equal to K, Q, S over R squared, R hat, where R hat is the unit vector. If it is a positively charged source charge, then the electric field is going to point away from it. If it's a negative point charge, it's going to point in toward it. Okay, just to remind you, there's our negative and positive point charges with our electric field maps. And the force exerted on a test charge, force on test, is equal to E times Q test. So if I were to put a positive charge here, it would experience a force along the electric field line toward the negative. If I were to put a negative charge particle, it would experience a force in the opposite direction of that electric field vector. Okay. So we're going to start off by looking at a dipole, which is a molecule that has a charge separation across it so that one end is negative and the other end is positive. It's like having 2 point charges that have the same magnitude that are separated by some distance, and their charges are opposite in magnitude and opposite in sign. So, a negative end, a positive end. Water molecules are thought to have a positive side and a negative side. Okay? Besides, isn't that cute Mickey Mouse head? Okay. So here I have a dipole. I've got a positive Q here, a negative Q here, and a separation center to center of S. Now we're going to look at two special points for the electric field in calculating the electric field. We're going to look at the electric field along the bisector, a line that's perpendicular to the connector line between the two charges that's smack dab halfway in between the two. So it bisects or cuts them in half. And then we're going to look at a point either down here along the axis of the dipole or out there above, along the axis of the dipole, either on the positive end or the negative end. Okay? So we're going to look at that midline, and then we're going to look along the axis. Now, let's look at the electric fields from each point charge along a midline. So if we're looking right here at that point in space, then we connect it, okay, center of this one to that point in space. The electric field from the positive point charge is going to point in this direction. From the negative point charge is going to point in this direction. So if you think about this, and let's see if this will let me do it. There's the x component of the E negative. There's the x component of the E positive. They're equal in magnitude, opposite in directions. They're going to cancel each other out. This angle theta is the same. So those two are going to be the same. They're going to cancel each other out. So all we're left with is an electric field vector that's pointing this direction. It's parallel to the dipole. The axis of the dipole is perpendicular to the midline. Okay? That's right of that. Now, if we're up here along the axis, okay, the electric field from the negative end is going to point downward. The electric field from the positive end is going to point upward. But if we look at it, the negative point charge is much further away than the positive point charge, so the magnitude of the electric field from the negative point charge here is going to be smaller. So the net electric field up there is going to point upward. We could do the same thing down here. If I chose a point, the electric field from the negative point charge is going to be there. The electric field from the positive point charge is going to point like that. The positive is going to be smaller than the negative because it's further away. Along the bisector, okay, cutting across the midline, strength of the electric field is equal to KQ. Q is what the magnitude of the two charges are, times S over R cubed. It's also sometimes written as QS over 4 pi epsilon 0 R cubed, where R is the distance out from the bisector, okay? And it points away from the positive end and toward the negative end. So, so if this was my positive, this was my negative, I'm out here along the bisector, okay? Why isn't it giving me red? Then our net electric field here points like that, okay? This is this R distance. S is this distance, okay? And Q is the magnitude of the charge on those two. Now, this allows me to mention something called the dipole. Or the dipole moment, okay? The dipole moment has a magnitude of Q times S, and it points from the negative point charge to the positive point charge. So, if I had my positive point charge here, my negative point charge here, it points this direction. Okay? Alright, let me erase. you can write the equation for the electric field as E equals minus Kp, the moment, the P vector over R cubed, or the negative P over 4 pi epsilon 0 R cubed. So if it's the negative, come on back down here where I want you. Boy, that jumped up. I'll get there. So that's one of my positive, that's my negative. My P always points upward. I'm out here on the bisector. Okay. Our electric field vector is this direction. So I can see they point in opposites. That's why we have this negative sign. Okay? So the moment, remember, is Q times S. And this dipole moment points from negative to positive. The electric field here points in the opposite direction. Okay. Note, K is equal to 1 over 4 pi epsilon 0, and epsilon 0 has a value of 8.85 times 10 minus 12 coulombs squared over newtons times meters squared. Now, along the axis, okay, E electric field at each end is equal to K times 2qs over R cubed, or you can say it's K times 2 times the dipole moment over R cubed, or 2 times the dipole moment over 4 pi epsilon 0 R cubed. So if you're outside along the axis, come on. P points in this direction, and E points in this direction. P points in this direction, E points in this direction. You're along the bisector, P still points up, E points down. Okay? And notice R is always measured from the center of the dipole. So the electric field vector points in the same direction as the dipole moment along the axis, outside of the dipole, and in the opposite direction along the bisector. So we're going to look at an electric field map for a dipole. Okay, so here's the negative end, here's the positive end. If you're outside and along the axis, it always points in toward negative, away from the positive. If you are in the middle between the two, okay, along that bisector, it points from positive to negative. And notice out here along the bisector, points from positive to negative. In between, positive to negative. And then out in these regions, it gets kind of wonky because you're now doing, some weird vector addition. Okay? So we're going to look at problem 3 on page 653 in the textbook. Okay, let's look at problem 3 here. It says, what are the strength and direction of the electric field at the position indicated by the dot? Specify the direction, the angle above or below horizontal. Now, we have a dipole here, okay? And our Q, our charge, is 3.0 times 10 to the minus 9 coulombs. All right? And our R is 5 centimeters, and our S is 10 centimeters. So that's 10 times 10 to the minus 2, or 1.00 times 10 to the minus 1 meters. And this would be 5.00 times 10 to the minus 2 meters for our R. Okay? And it says, what's the strength and direction of the electric field? So we're going to use our handy dandy equations. So let me flash them up on the screen so that we can use them. Okay, the equation we're going to use is this one. E is equal to K QS over R cubed. So let's set this sucker up. So the magnitude of E is going to equal K, magnitude of Q, times S over R cubed. So 8.99 times 10 to the 9 newtons meters squared over coulomb squared times Q, which is 3.0 times 10 to the minus 9 coulombs, times S, which is 1.00 times 10 to the minus 1 meters, all over 5.00 times 10 to the minus 2 meters cubed. Okay? So 8.99 exp9 times 3 exp9 negative times 1 exp1 negative divided by 5 exp2 negative raised to, wait a minute, 5 exp2 negative raised to the third power. Okay, 1 over that times 8.99 times 3 times 1 exp negative. So I get an electric field strength here to be 2.16 times 10 to the 4 newtons per coulomb. Okay, and if we look at it, okay, it is going to point from the positive to the negative. So the positive here, the negative here. We're out at this point, it's going to point this direction. So it's pretty much a plug and chug question. Okay? All right, now let's see what the other question was that I had put in here. That. Okay, that was the only problem I had at this time. Okay. Hope you guys aren't getting dizzy. Now, the next thing we want to talk about are electric field lines. Okay? Electric field lines are lines used to pictorially represent the direction and strength of electric field in a region of space. When we draw electric field lines are continuous curves drawn tangent to the electric field vectors. That means the electric field vectors are always parallel to electric field lines at a point in space, or you can say they're tangent. They point along the tangent line. Okay? Further apart electric field lines are, the weaker the electric field. Electric field lines always start at a positive charge and always end at a negative charge. Electric field lines never cross. The number of lines leaving a charge or entering a charge are proportional to the size of the charge. So here's an example of electric field lines around a dipole. Okay? Notice that there are as many field lines leaving the positive charge as there are entering the negative charge. And that if I looked at this, okay, along the bisector, notice the further that I go out from the connector line, the smaller the strength of the electric field is, the further apart the electric field lines are. Okay? And notice that they point in down here at the negative and they point out at the positive. You can see electric field strength is going to be really strong close in, and it weakens as you move away. So if I were to look at this point, so if I were to look at a point here, I am going to make friends with this sucker, I promise. Now it wants to draw. So if I were to pick a point, I'm going to use my finger here, and I pick a point here, I can see the field lines are closer together there than here, so I know the field is stronger here than it is here. So we're going to look at a couple of conceptual questions on page 365 and 635 and 652. So 635. So if we look at this conceptual question, it says, at the dot, the electric field points. Okay? Well, we know the electric field relative to this point charge would go this way, that point charge would go that way. They're the same magnitude of charge, they'll cancel each other out. The electric field from this negative point charge is going to point up. So the net electric field at that point is going to point up. Now let's look at the other problem I wanted us to think through. Okay? It's question on 652. It's one of the conceptual questions at the end of the chapter. So if I look at problem 3, it says rank in order from largest to smallest the electric field strengths. Okay? Now, we have electric field lines. So I'm looking at how the electric field lines are spaced. Largest to smallest. Well, the electric field is going to be the strongest where the lines are the closest together. So 3 and 4 are equal to each other, and they're the largest electric field. Then 2 is going to be next, and 1 is going to be last, because that's where the electric field lines are furthest apart. So I want you to be able to look at electric field lines and know something about relative strength of your electric field. two positive charges that are sitting fairly close to each other. One of the things I want you to notice is this dead zone. Because here, the strength of the electric field, smack dab in the middle, they're pointing in opposite directions, equal in magnitude, they cancel out. There's no electric field here. So notice how it bends outward. If you were to replace these with negative charge, it would look exactly the same, except the arrows on the field lines would be pointing inward. Okay? Now, most cases we don't see a single charge. We don't even see a single dipole or 2 point charges side by side. Let's think about 3 point charges side by side, and then we're going to start expanding out. So if I had 3 positive point charges side by side, and I was looking at this point in space, okay? I would know that there would be an electric field from point 1, an electric field from charge 2, and an electric field from charge 3. One of the things I want you to notice here is the magnitude of the electric field from 3 in the y direction and from 1 in the y direction are going to cancel each other out. So when I add up the electric fields from these 3 point charges at this point in space, it's going to point outward. Okay? So the y component of the electric field of 1 and 3 cancel out. And if we start extending this out until we start adding more and more charges, we go from 3 to 5 to 7 to 9. Every time, okay, the 2 point charges that I've added on either side, their y component of the electric field is always going to cancel out. Now, if we have an extended line of charge, we're going to talk about the line of charge as having a linear density, lambda. Lambda is equal to the total charge on the linear object divided by its length. Or you can say lambda is Q divided by L, which is charge per unit length. Okay? So if I had something that was L long and it had a total charge of Q, then lambda would equal Q divided by L. Now, if I'm at a distance d from that linearly charged object, like a wire or a rod, okay? Each of these little, I could think about taking this, I could think about taking this and dividing it up into hunks. Each of these hunks is going to create an electric field at that point in space. Okay, and we know that all of the y components are going to cancel out. And no, my drawing is not perfect, but you get the idea. Okay? So we divide the rods up into segments and think about the electric field created by each segment. We know that the y components are going to cancel out, only the x components are going to remain. Okay? For a rod of length L, if we look at summing up all of the x components, we can get the following equation. For a rod of length L, if we are a distance r from the rod, E is going to equal K, the magnitude of Q, R square root of R squared plus L over 2 squared. Okay? Now I didn't do the derivation of this, but you can find the derivation of this in the book, so I'm not going to beat you over the head with this. Okay, so this is for a rod of length L. Now, if I have a positively charged rod, then the electric field is going to point away from it. If it's negatively charged, it's going to point to it. When our line of charge approaches infinity, So as L approaches infinity. Okay? Our equation above, okay? So that r squared plus L over 2 approaches L over 2 squared, because r becomes inconsequential compared to L over 2, so that we get strength of the electric field is equal to KQR times L over 2, or 2KQ R over L. Well, Q over L is lambda, so K2 lambda over R, or you can see it 1 over 4 pi epsilon 0 2 lambda over R. I usually stick with this one, but your book likes this one better. And this becomes the plug and chug equation if you have a infinite line of charge. So let's look at stop and think on page 639. We're going to look at stop and think 23.3. So 639. Okay. Which of the following actions will increase the electric field strength at the position of the dot? Make the rod longer without changing the charge. Nope. That lowers the charge density, that decreases the value of lambda. Make the rod shorter without changing the charge. That would increase lambda, that would do it. We would increase the strength of the electric field. Make the rod wider without changing the charge. That's not going to do anything. Make the rod narrower without changing the charge. It's not going to do anything. Add charge to the rod. That will increase lambda. That would increase the strength of the electric field. Remove charge from the rod. That would decrease lambda. That would decrease the strength of the electric field. Move the dart further away. Well, if we move the dot further away, that's going to decrease the strength, because we know that the strength of the electric field drops off as a factor of R. And we move it closer, it should increase the strength. Okay? All right, now. Switch back. The electric field vectors then around the line of charge are always perpendicular to the line of charge. And if it's a positive charge on the wire, it's going to point out. If it's negative, it's going to point in. Okay, just reminders. And let's look at problem 8 on page 653. Guys, as we read problem 8, okay, it says the electric field strength 10 centimeters from a very long charged wire is 2,000 newtons per coulomb. What is the electric field strength 5 centimeters from the wire? I don't have that lined up very well. I apologize, guys. So there's our problem. All right. So that we're told that the strength of our electric field is 2,000 newtons per coulomb at 10 centimeters. We want to know the strength of the electric field at 5 centimeters. Okay? So let's move over here so we can look at the board. So let me get this cleaned off. Got some room to work. Okay. E, the strength of the electric field, is equal to 2K lambda over R. Okay, so I've got 2,000 newtons per coulomb is equal to 2K lambda over 10 times 10 to the minus 2 meters. So I can say that 2K lambda is equal to 2,000 newtons per coulomb divided by 10 times 10 to the minus 2 meters. So 2,000 divided by 10 exp2 negative, that's 2.00 times 10 to the 4 newtons over coulombs times meters. And I want to know the strength of the electric field when I'm at 5 centimeters. So I just have to go 2.00 times 10 to the 4 newtons over coulombs times meters divided by 5 times 10 to the minus 2 meters. So I get 4.00 times 10 to the 5 newtons per coulomb. So when we were in closer, we got something that was stronger. And that's all we had to do for that problem. Now, was there another problem right there that I wanted us to do? Nah. That's the only one with a line of charge I wanted to do as an example. Okay, guys. Now our next charge distribution up to bat is a plane of charge or a disk of charge. To begin our journey, I'd like us to think about taking our plane of charge and cutting it up into rings of charge. Okay, we're going to look at page 640 as an example problem. We're going to look at example problem 23.4 and think about having rings of charge and looking at the electric field at a distance z from the ring. By looking at the sum of the electric fields for all of the parts of the ring, we can get an equation for the strength of the electric field at a point z from the surface of the ring. Okay? I think I have it back. Yeah. Now, if I had a ring of charge plus charge, then it's here in the xy plane, and we're looking at a point z from the xy plane. If I looked at this point and this point, and I added up their electric fields, the x components of the electric fields and the y components of the electric fields would cancel out each other, and only the z component of the electric field would remain. Okay? So the x and y components are going to cancel each other out. Now, if I did this for each segment, okay, the electric field caused by just that ring is K, Q, Z over Z squared plus R squared, where R is the radius of that ring, okay, to the 3/2 power. Now, we're going to add all of those rings up. And I want you to notice when Z is 0, the electric field is 0. Because if you were looking inside the ring, that point in the middle, everything's going to cancel out. Now, if we were to assemble the rings into a disk, and we were to add up all of the electric fields from all of the disks, perpendicular to the plane of the disk. Okay? So we divide the disks up into little delta R's, and we add it up. For a plane of charge, okay, we're going to talk about its surface charge density, eta, which is Q over A. We can write the following equation. The electric field is going to equal eta times 2 epsilon 0 times 1 minus Z over the square root of Z squared plus R squared. Okay, that was gotten through calculus. I'm not going to make you do the integration there, okay, but we got that through calculus. If the charge on the plate is positive, then the electric field will point out from the disk, and if the charge is negative, the electric field will point inward. If we're now to increase R to infinity for an infinite plane of charge, becomes a very easy equation. E, the strength of the electric field, is equal to eta over 2 epsilon 0. Because let's look at this guy. As R approaches infinity, then this guy is starting to approach, well, this is starting to approach 0, and 1 minus 0 is 1. Okay? So this is going to approach 0, so you're left with just the 1 as R approaches infinity. Okay? So the magnitude is equal to eta over 2 epsilon 0. For a positive charge, it's going to point away. For a negative charge, it's going to point toward. Note the electric field strength for a infinite plane of charge does not drop off as you move outward from the plate. It remains constant, and the direction remains constant. And as long as we're not far away from a plate of charge and we're near the center of the plate, we can treat almost any plate of charge as if it were an infinite plane of charge. Okay, so let's look at problem 16, and then I think we will probably take a break. Okay, and I'll hit the next section of the chapter. So let's look at problem 16. Okay, if we look at problem 18. I'm on problem 16. There it is. It says, it's a parallel plate. I just want a single plate. Let me see if I've got a single plate problem, because I don't want to do parallel plates yet. Yeah, I'll hold off on doing a problem with a plate until next lecture. Okay, guys, we'll finish off this chapter in the next video.